Alright, so in this section we're going to try to discuss how we find the area of a region whose boundary is going to be given by one or more polar equations. Right, so we may take the circles or the roses or stuff that we had from last time. Those will be our polar equations. They'll bound some region, and then we're going to try to find the area of that region. The other thing that we'll do later on is we'll try to find the length of some part of the curve or the entire curve when that curve is given to us as a polar equation. So the first thing I want to recall is that when we were in geometry, the course we all love, we were taught the area of the sector of a circle. And so the sector of a circle is kind of like we take a slice out of it right here. This will be our radius, some degree measure theta. And so the sector is going to be all of this light blue area, right? So this entire slice. And we were told, so this part right here is given to us as r theta. And so the area of this sector is going to be 1/2 r squared theta. So now imagine we have some rays theta equals a and theta equals b. Right, so it's going to be something like this. So here's theta equals a. And here's theta equals b. And suppose we have some polar curve r equals f of theta. So something like this. Then what we're trying to find here is what is the area of this region. So this dark blue area, this is our region, this capital R. Okay, and so the idea here is that we'll take, so I'll show you down below. The idea is that we'll take this region, let me draw it again. And we'll partition it with slices. And so if I just take slices like this, then the idea would be to take these and then start calculating these as the area of a sector. And so once we start taking infinitely many slices, then we will get this formula for our area, which is going to be the integral from theta equals a to theta equals b of 1/2 r squared d theta. Now, for example 1, let's see how we use something like that. So we're asked to find the area of a region that is bounded by some important piece of information is our r equation. And then the second important piece of information is where are we integrating. So we have a is equal to the integral from a to b of 1/2 r squared d theta. So this will be equal to, so let's see, our a is going to be pi over 2. B will be 2 pi. We can pull the 1/2 out. And then r, that's theta inverse, so this should be theta inverse squared d theta. So this gives us 1/2 times the integral from pi over 2 to 2 pi of theta to the -2 d theta. And so integrating this, we should have, so we add 1 and then divide by the new exponent, so it's -1 over theta from pi over 2 to 2 pi. And so then this would be -1/2 times 1 over theta, so we go from 2 pi, so 1 over 2 pi, minus, now we plug in pi over 2. And then if I multiply my 2 out on bottom and my -1 on top, I'll get -1 over 4 pi plus 1 over, so if I do 2 times pi over 2, that'll just give me pi on bottom. So this would be the area of that region. now let's take a look at example 2, which is going to be a little bit more difficult. So again, on this lecture, I'm going to leave a lot of integrals for you to do. I'll leave you the answer so that you can make sure you're getting the correct answer, but this is going to be a good time for you to practice techniques of integration for our upcoming final exam. So we know that the area is supposed to be the integral from 0 to pi. We can pull out the 1/2. We'll have r squared, so it's going to be sine of theta plus cosine of theta squared d theta. So just to give you an idea of how this should work out, so spoiler alert, the answer you should get will be pi over 2. But the idea of how this is going to work out is you'll start by FOILing this out, and then we should get a sine squared plus cosine squared. That's going to give us, that'll be 1. And then we'll have plus 2 sine theta cosine theta. And so you'll want to split this into 2 separate parts, and then you can do a u substitution on the sine theta cosine theta part. Okay? So go ahead and practice that. If you run into an issue and you get stuck, please feel free to come to office hours and we can discuss it. Now let's look at example 3. So for example 3, just getting an idea of what this looks like. The pictures aren't too important right now, but they will be important later. So we know that 2 sine theta from our last lecture, this is just going to be a circle of radius 2. So we already know what this is. This is the area of this should be pi r squared. So the answer we get here, this is not a radius 2 circle. So this up here will be 2. The circle is actually going to have a radius of 1. So the area we get here should just be pi. But we'll use our new method to actually verify that. So we should have a is equal to 1/2 times the integral. Now remember, last lecture I was talking about what does it take to generate this full circle. And I said this was going to be extremely important. And this is why it's important. Because they don't give us what theta should be here. But we know that this is generated, right? We get the full circle whenever theta goes from 0 to pi. And so that's why we're integrating from 0 to pi here. And so then this should be 2 sine theta squared d theta. So again, you'll want to square that. You're going to have to integrate sine squared of theta, so this will be a good time for you to practice the trig integrals. And so spoiler alert, you do end up getting that the answer is pi, just like we thought it should have been from our geometry formula. Now let's look at example 4. Here, this is not a plus a sine theta. However, it is still going to be a cardioid. Okay? So for this cardioid, there's something special we can do. Alright. So notice, if I graph this out, so when theta is equal to 0, we get r equals 4. So I'll get a point right here. When theta is equal to pi over 2, I'll get 7. So that'll give me, let's say 7's way up here. When we have theta equals pi, that'll give me 4 over here. And then when theta is equal to 3 pi over 2, we'll get 4 minus 3, so that'll give me 1 right here. So this cardioid is going to look something like this. That may be the best drawing I ever do in my life. Okay. But what I think is interesting here is noticing that, okay, this is at theta equals negative pi over 2, or 3 pi over 2, however we want to call it. And this is going to be at theta equals pi over 2. And so notice that this is symmetrical about the y-axis. What this means is that if I want to find the area of this, I can just find the area of this one region on the right-hand side and multiply it by 2. So that's why our area is going to be 2 times the integral from negative pi over 2 to pi over 2 of 1/2 r squared d theta. So I can pull that 1/2 out, and we'll get the integral from negative pi over 2 to pi over 2. Let's see, r squared, so that's going to be 4 plus 3 sine theta squared d theta. This will be another good time for you to practice integration techniques. So here, what I recommend is you're going to get 3 parts, right? You'll get a number. You should get 16 plus 9 sine squared theta plus 14 sine theta. And so you'll want to integrate those one at a time, right? So integrate the 16, that'll give you 16 theta. Then you can work on integrating the 9 sine squared theta. That'll be a trig integral. And then you can work on integrating 14 sine theta, which will just give you negative 14 cosine theta. Okay. Once you're done with doing all of that, your answer should give you 41 pi over 2. Right? So notice if I just asked for half of the area of this cardioid, then we would have removed this 2. But since we want the area of the entire cardioid, we put the 2 in there. Okay, now let's take a look at example 5. So for example 5, now this time we actually have a proper cardioid. From last lecture, we know that this cardioid is going to look something like this. Okay, and we were told last time that this gets generated, right? We get the entire cardioid whenever theta goes from 0 to 2 pi. So it tells me that my area is going to be given by the integral from 0 to 2 pi of 1/2 r squared d theta. Okay, here I could use properties of symmetry to go about this, but I want to show you it works either way, right? If you notice the symmetry, you can use that to cut down some work. If you don't, then you just need to know what generates this entire cardioid. Okay, so this should give us 1/2 times the integral from 0 to 2 pi of 1 minus sine theta squared d theta. And that will be equal to, your answer should give you 3 pi over 2. Okay, so again, FOIL this out and then maybe break it up into parts, and that's generally going to be the way that we handle most of these. And I'm not saying integration by parts where we have our u and v prime. I'm saying break it, use the fact that when we add things together and we're integrating, we can integrate them separately. Okay, now suppose we want to find the area in between two polar regions, right? So suppose we have something that looks like this. So here's a ray that will be theta equals A, and here's another ray that will be theta equals B. So now let's put in a f of theta and g theta equation. So let's do something simple. Let's say this is our f theta equation. And then let's say this is our g of theta equation. And so then what I'm looking for, our region R, is going to be this light blue region in here. Okay, so then, actually I need to switch this up real quick, just because of the way the formula is written. Okay. So the way you find the area of this is you're going to integrate from theta equals a to theta equals b. So that's this part. And then you'll still have the 1/2. But instead of r squared, what you're going to be looking at is the function with the bigger radius. So notice, right, if I take a line, what's a good color to use? Say I take this line right here. Notice that the green function is further from the origin. So whichever one is further from the origin, that one will come first, and you'll square it. And then you'll do minus the other one and square that. Okay? So let's practice this on example 6. So for example 6, we're trying to find the area of the region inside the circle r equals 4 sine theta, and outside the region given by r equals 2. So let's graph this to get a good idea of what this looks like. 4 sine theta, so we'll represent that with green. If this is 4 up here, we know it looks something like this. Okay, and then the region r equals 2, well, if this is 2 right here, then that will look something like this. So then the area that we're trying to find is this area right in here. So then my rays that I'm looking at for theta are going to be wherever these intersect. Right, so this would be my theta equals A, and this is going to be my theta equals B. Now what I'm going to do here to cheat and kind of reduce some of the work is I'm going to notice that this region is symmetrical about the y-axis. So really what I'm going to do is I'm going to cut it off right here. We're just going to find the area of the region on the right, and we can multiply by 2. So this is at theta equals pi over 2. So the area that I'm actually trying to find is this region in here, and we'll multiply it by 2 to get the total region. Okay, now to do that, I still need to figure out what this intersection point is. To do that, I'm going to set the two curves equal to each other. So I'll take 4 sine theta and set it equal to 2. Well, that means that if I divide by 4 on both sides, we get sine of theta is equal to 1/2. We know that happens when theta is equal to pi over 6 or 5 pi over 6. Now, since we're doing this for theta equals a, we know it's going to be the smaller one. So our a is going to be pi over 6. Okay, so just like I was saying before, our area will be 2 times the integral from pi over 6 to pi over 2. And now we use our formula, which is that this should be 1/2 times, so we take the function with the bigger radius, so that's our green one, so that's 4 sine theta, and square it, and then do minus the one with the smaller radius. So it's going to be 2, and we square that. And then d theta. And once you integrate this out, this should give you 2 pi minus 2 pi over 3 plus 2 root 3. Okay, so the big thing here is just knowing this formula. Okay, I could have done this, if I take this 2 out, I could go from pi over 6 to 5 pi over 6. But I just think that working with pi over 2 is nicer, especially because, I mean, you know, sine of theta, if theta is pi over 2, then you get 1. If you have cosine of theta and you're using pi over 2, well, then you get 0, and that's even nicer. Okay. Now let's take a look at example 7. So example 7 here, it looks like we have a circle and a cardioid. All right. Well, we know what both of these look like. This green curve, so if this is 1, 2, 3, then the green curve is represented by a circle like this. And for the other one, this should be something that looks like this. Okay, so then the area that we're trying to find is going to be this area in here. So again, what I'm going to do is I'm just going to look at this top half, and then we'll multiply by 2 since this is symmetrical about our x-axis. Alright, so clearly this theta isn't too bad to find, right? This is happening at theta equals 0. But now I need to figure out, okay, well, what is this theta right here where they intersect? Okay, well, to do that, we'll set the two equations equal to each other. So we'll have 3 cosine theta is equal to 1 plus cosine theta. If I subtract a cosine theta on both sides, that'll give me 2 cosine theta is equal to 1. So then cosine theta must be equal to 1, which means that theta is equal to, well, our possibilities for that would be pi over 3, or, so notice I'm saying or because there is another place where we get cosine theta equals 1/2. But I don't have to worry about that because pi over 3 is going to be the one that lies in this quadrant right here. Right, in quadrant 1. So then we get theta is equal to pi over 3. So then our area is going to be given by 2 times the integral from 0 to pi over 3. And now we use our formula, so we should have 1/2 times the function with the bigger radius. So it ends up being our 3 cosine theta squared minus the function with the smaller radius. So this will be 1 plus cosine theta squared d theta. Okay, now for this one, you don't have to worry about solving this one out. This one would take quite a bit of work, and I don't think that the amount of time that this problem takes to solve is worth it to practice for the final exam. Right, we won't have stuff of this difficulty on the final exam. But again, if you did want to solve it, the general idea is square both of these, cancel out terms, and then integrate piece by piece. Okay, and also notice that this question, we're only asking for the integral that represents the area. So make sure you're paying attention on exams and stuff. When someone asks for the integral that represents the area, you don't need to find the actual number. Alright. Now let's look at example 8 before we move on to finding length. So this one asks us to find the integral that represents the area inside one loop of the polar curve r equals sine 3 theta. So we know what this graph looks like. Since our k value is odd here and it's sine, I know that it's going to look something like this. And so what I'm going to do here is I'm just going to be trying to find the area of this region. Now, a key thing to notice, actually, let me use a different color. So I'm trying to find the area of this region. A key thing to notice is that this loop is actually symmetrical. If I take a line here, then this will split our loop in half. Okay? Now, if you refer back to our previous lecture, we actually found out that this happens at theta equals pi over 6. the way to think about that is, when is this radius going to be the largest? Right, because we can tell at this outer point on our loop, this is going to be one of the 3 farthest places from the origin. So we're kind of looking at, when is sine of 3 theta going to be the biggest? Well, that's when sine of 3 theta is equal to 1. Right? Now we know sine of theta is only equal to 1 at pi over 2. So we're kind of solving for, when is sine of 3 theta equal to 1? Well, it's kind of like saying we want 3 theta to be equal to pi over 2. So that would mean that theta is pi over 6. So to get the area of this, we're just going to focus on this lower half. So I can go from theta equals 0 to pi over 6. So this will be a equals 2 times the integral from 0 to pi over 6 of 1/2 times. So now here, notice I only have one curve, right? So I don't need to use this new equation that we've learned where it's the bigger radius minus the smaller radius. So this is just going to be 1/2 r squared. So this is sine squared 3 theta d theta. Okay, and that will be the integral that represents this area. Now for our next topic, we're looking at finding the length of a polar curve. So to do this, we'll be using, if we have some polar curve given by r equals f of theta, and theta goes from a to b, the way we find this is we integrate from a to b, and then we'll have the square root of r squared plus the derivative of r squared. So to show you what this looks like, so here I know that the length is going to be given by the integral from 0 to pi over 2 of the square root of r squared, so it's going to be theta squared squared, plus, so the derivative of r, which is going to be 2 theta squared d theta. Okay, and when you calculate this out, you should get that this is going to be equal to 1/3 times, let's see, this should be pi squared over 4 plus 4 to the 3/2 minus 4 to the 3/2. Okay, again, another opportunity to practice for the final exam right here. All right, and then for our last question, we'll be looking at finding the integral that represents the length of one loop of r equals cosine 2 theta. So we know that r equals cosine 2 theta. We have k is even, so we should have 4 loops. Since it's cosine, the first one starts on the x-axis. Okay. Now again, this is symmetrical. So what I'm looking at, instead of going from, so the way this would work, instead of going from theta equals negative pi over 4 to theta equals pi over 4, we can just go from 0 to pi over 4. Right. The reason for that is that if I just take this part, find the length of it, that would be the same thing as if I just found the length of this part right here. So I'll just find the maroon part and then multiply it by 2. So using our formula, we have that the length is going to be equal to the integral, so 2 times the integral from 0 to pi over 4, the square root, so we should have r squared, so it'll be cosine squared 2 theta, plus, so now I need the derivative of r, so dr d theta. This will be equal to negative sine 2 theta times 2. So this will be negative 2 sine 2 theta squared. Okay, and that will give us, d theta, the integral that represents the length of one loop of this polar curve. All right. So again, please practice these integrals except for the ones where it says find the integral that represents. For all the other ones where I actually left answers, please solve those out. If you have any questions, please come to office hours and ask me about them. Hope you have a great day.